connected to TV, but it's not working.
I thought it was just now on.
It's on, but
I know maths is still sick, is it? Yeah. Okay. 1, 2, 3, 4, 5, 6. Any general comments? I have comment. You will not have class on. No class. So there was this discussion, we said that we have a. I might ask you guys to lecture, and so I considered it and I said, we will just drop the class completely. You're welcome to come and help me with the. There are 500 students coming to the Bantera Center, which is also called the SIU Arena. That's a stadium that you see there where football. It's all often, no, not football, right?
basketball.
Basketball, yes. Yeah, so it's an inside indoor stadium. And it's probably in the front side of it. You're welcome to come and help with the demonstration, but that's not a requirement for the course. So it's just a voluntary basis. Okay. That's make it simple. So, so for the class, there's we have a homework that was due, so there is no homework as such posted, but I will be teaching Green's function now, and you will see a homework that is coming up soon. So homework 8 will be due on the next Tuesday, next Tuesday, so 28th, and it will be April 4th, right? So that's not yet posted to my knowledge. Is it homework 8 or 9?
8.
8, okay. I'm not confused. No, homework 8 is already posted, so this is homework 9. Yeah, so. So homework 8 is due. How about that? Yeah, I should also. This is better. 28, we should make it 30 now, right? That's no class on Tuesday. It's basically meant for Tuesday, but it has been postponed to Thursday because that's. Of the 2 classes we will study today and Thursday, there's a homework 9 and midterm 2 is. April. Did I cover everything? Is that consistent everything? Okay.
You said something about March, April 20th for having 2 exams for you.
I think that was a confusion on my part because I think it's on April 17th, I suppose.
Oh,
Yeah. So there's an exam on 17th and 18th, I guess. Yeah, but still, that doesn't change. And whenever I write something, if it's written on the syllabus, I try not to change it. If it's 2 exams, I deal with it. I've been trying to not have more than 1 exam on the same day. But then the final exam, I am, at least for me, I have 2 exams, but that's easier than you guys do exams on the same thing. Okay,
Jason, can we stop recording on next session?
oh, sure.
If someone else want to do it. 'Cause
Oh,
sometimes
it's too much pressure on you, yeah, which is very understandable. If I were in your place, you cannot skip classes. For all you know, I think I can understand, I appreciate it, and yeah, sure, so the question raises. We can either drop recording or someone comes
someone
ahead and
volunteer.
comes ahead and does it. Well, is that question clear, what our Aryan is proposing?
Or
Recording.
No, from tomorrow, today onwards, like today and going forward. We can stop having the recording altogether. That's one option, that's the easiest option. But if you think recording is helpful, then someone has to step forward and learn this setting up. It is fairly straightforward.
We can also take turns every session. So-
Taking turns, I don't say that because then there will be confusions as to who is in it. So someone has to come up and you can relegate the duties to someone else, but someone has to take the responsibility of the, so Monica, you,
Okay.
yeah. And again, feel free to stay absent on that day, but you have to relegate the job to someone else. Yeah. I think in graduates programs, it's easier, but undergraduates, I'm sympathetic towards them because many really want to skip classes. Not because they want to enjoy or something, they have other things, and once you are stuck with these things, you cannot skip classes. So, okay. Okay, so we're still having recording listings from what I understand. Okay. Okay, we want to come back to the standard way of doing electrodynamics, or standard, or there's nothing non-standard as at the graduate level. Submissions. Sorry, thank you very much.
so on quiz question, we were supposed to get 2 Maxwell equations, right? The del B and the other part.
What is the dual force measure?
Yeah, we like when we is equal to 0 and I, the 2 equation, Maxwell equation is supposed to be. Like W nu, F mu nu, from that one, we are supposed to, so like when mu is equal to 0.
Oh, yes.
So we are supposed to get Maxwell equations. So we are I don't know about others, I got del dot B. The other one, I have -1 OC part remain.
Didn't we do that in class?
No,
We did
We
not
did
do
the
the
last part.
class, yeah, I skipped that, I said that fill in the blanks, kind of. It should work out, yeah, let's quickly do that. Yeah, so you're saying, if you have, let me do it here. D mu F tilde mu nu is equal to 0, that's your Maxwell's equation. You are interested in the scenario when mu is equal to I. Yeah, so that's what we are interested in. So this is B nu F tilde I mu is equal to 0. That's the 0. And remind me, what was F tilde I 0? And what was F tilde I j?
so F tilde 0 I is BI, so we can get the minus of it.
So minus
Yeah, Pi
and this one would be,
by this epsilon I j k.
this will be epsilon I j k
So there's a minus one O C also.
minus one over c.
Yeah.
Okay, so this is d zero, so that's one over c d by dt. F I zero is minus b of I plus j epsilon, so it's minus one over c epsilon I j k k is equal to zero. So c goes away and minus sign goes away. So plus epsilon I think that's it.
Yeah,
So,
yeah.
plus
Okay.
okay,
Yeah.
so maybe one of the C's will come. Any other questions? Yeah, notice, what was, if you were to think about the formal description of electrostatics, we say that a charge, so a summary, right, of electrostatics. Electrostatics. You say there is a charge. Let's say Q1. It creates an electric field. And you say the electric field it creates is E1 is equal to 1 over 4 pi epsilon naught times Q1 over, let's say observation point is R minus R1, which is the position of the charge. And this is Q, or let's say Q. And then there is R minus R1. That's your electric field, if you want. And then there is a force on another charge, electric force. It's F Q1, which is on another charge, which is Q2 times the electric field due to 1. The electric field at the position of the second charge. This is R2. Electric field 1 is at position R. So you're evaluating the electric field at the position of the second charge. So that's summary of the whole of electrostatic if you want. And if you know it for one charge, you can do integrations and do this for many charges. Continuous distribution is integral over all the charges. And in that integral, one is a central role played by Green's function, and that was basically the electric potential, call it the Green's function either. So the electric potential was V due to a single point charge is equal to 1 over 4 pi epsilon naught times Q over R minus R1. Right. This is the electric potential at position R due to the charge at position R1. This is nothing but the Green's function. Okay, so this is the Green's function, and there's an equation we will see. And once we know that, everything else is tedious repetition. You have 1 point charge, second point charge, you say you keep adding on to that. So this is linear differential equations. Once you know it for one charge, keep adding on to that for your multiple charges. It's all. Rest is tedious calculation. Same thing with magnetostatics. What is the source for magnetostatics? Current. Good, very good. So current, or let's say moving charges, but current is good, better. the moving charge or current. So you say moving charge is Q1, right? So times velocity, the velocity of moving charge, or as you like to say, so this is current in a wire. So this is an infinitely small, so there's a wire, and this is a small stretch of this wire. Right, that's your DL. And differential length typically does not have any direction associated with it, but this direction is from the current I. So when I say I times DL, the vector there is associated with the direction of the current, not of the length itself. So that's your source of magnetic fields. Clearly, if velocity is not there, it's gone. So you can get rid of the magnetic field. If you want to escape magnetic field, just make the charge that is creating the magnetic field go to red, or you start moving with the same velocity, and in that frame, magnetic field can be gotten rid of. So it's very related. So what's the magnetic field due to that? Any piece of wire or a moving charge is equal to good. Mu naught over 4 pi and
I cross. I currently here.
I1 DL over R. It's pretty much the same. R minus R1 cube. And that is R minus R1. See that almost exactly the same, except
This is the Biot-Savart law.
Biot-Savart law, very good. And what is missing in this?
The integral.
Let's say dB
Okay.
or point charge, right? So this is a tiny differential element.
Okay.
So what's missing in this?
The dimension are the same.
Dimension are the same, I think so, yeah. That's dimensionally correct,
The angle
or
Cross.
the cross product, right? The two vectors, I haven't told you which, is it a cross product or a dot product, this is a cross. That's a cross, so notice that's the only difference, so the source now has a direction. Source of a magnetic field has a direction of the velocity. So in that sense, it is it's a lot more tricky to visualize source and the observation point of view. Or it's a matter of difficulty always. Perspective. Magnetic field or magnetic force, right? Magnetic force. So here we talk about forces between charge Q1 and Q2, right? You meet two charges, there is a force between them. In this case, what are the forces? Two wires, there is a force. If you have an electric wire 1, electric wire 2, both carrying currents, there is a force between them. And we can calculate that. So this is force F on the second differential element from the first differential element. It is I2 times DL, so let's say this is the differential force, right? It's DL2, DL1, cross with the magnetic field of the first differential element at the position of the second one. Notice this is evaluated at the position of the second one. And one can do this calculation, and we do this for simple scenarios where there are two parallel wires or two anti-parallel wires, and they attract a repel. And one of the important things that come up with here is that like charges repel and unlike charges attract. Here, like currents so here, like charges repel, like charges repel. What's the statement here? Like currents, is that question clear what I'm asking? Attract, they're opposite. They're pretty much opposite, and that's because the interaction energy in that scenario has an opposite sign, and that has conceptual depth to it, but we will not go in there. But what I was trying to say in the whole, what I'm trying to motivate is that this whole thing comes from the point chart. Once I know the point chart, I can build everything else. What is the Green's function for magnetostatics? By that, what I mean is, so this whole problem can be converted into a rewritten in the form that is the electric potential phi of R is equal to Q over 1R times delta function of R. Is that clear? Maybe rewrite it. Yeah, this one. Okay. Is that clear? So that's a potential. And you immediately say, right, that, oh, that is a Green's function associated with this. And you call that Green's function G of R is equal to, this is, I need to call this, let's call this G naught, however, because this is statics. I'm going to change this Green's function. That's what this course class is about, right? And this is simply remove that constant, and that's called the Green's function. So this is the Green's function for electrostatics. That's again, Green's function is nothing but the electric potential due to a point charge. Okay, that's all. And mathematically, it's called that. Remove some dimensions of it, and that's what it raises the question: what is the Green's function in magnetostatics? Or this point charge, what is or moving point charge, what it is, and yep.
Should satisfy for the A.
Yeah, what is the equation satisfied by A? That's the first question you will ask.
It should give us curl of A, should give us B.
A will give us
Curl of
B.
A.
Curl of A will give you B, but I'm asking what is the equation satisfied by A?
A.
Or maybe I think I should say this in a better way. This is rho, right? I think that's better. This is rho over epsilon, charge density. And for a point charge, when I remove the Q there, epsilon naught there, you get this. So that's your phi amperes. No, amperes. Yeah, but yeah, that's del dot del cross H is equal to amperes phi is del cross H is equal to I, right? But you want it in A. What is the equation satisfied by A?
A is equal to mu naught K.
Very good, right? So this is minus del square A. Notice the similarity here. It's very much the same. Right? Pretty much the same, except there's a scalar, it's a vector. Scalar source, vector source. J is Q times V. Right? I times dl, it's all the same. So what's the Green's function for this? For magnetostatics? It's the same. It's pretty much the same. Because once I remove the vector, the vector source and this part out, whatever is remaining and dimension is out, it's exactly the same. There's nothing new as far as the very ingredient that is contributing to the electric and magnetic field in statics. So it's the same Green's function. Okay, and if you remember, how that comes into picture is your vector A of R, or like if let's go in here, right, phi. If I know for one point charge, how do I do it for rest? You just integrate over all the sources, and that is got by rho of R prime over integrate over all of them, right? So it's R minus R prime. And then the 4 pi epsilon. Right, integration over all the choices, that's your point charge. Integrate over all of them, you get phi. How do you do it here? Same thing, exactly the same thing, except this time you do it for currents. J of R prime, and it is 4 pi times R minus R prime. That's it, whatever you need now. Same thing remains, and then when you get the magnetic field, it comes the curl. Curl of the A is magnetic field, and that's where the cross product comes in. But at the field level, at the potential level, they're identical. Right? One is having a scalar source as far as the rotations goes, and the other is having a vector source to it. That's all statics, right? What is missing in all this is that it is static, things are not moving, right? We want to go beyond this and bring in the full electrodynamics, and we want to talk about electrodynamics in principle, at least in the situation where the charges are not getting affected by the magnetic field. The magnetic field is created by the charges, but they don't affect the charge again. That is a back reaction. So it's throwing away the radiation, but the radiation is not affecting the charge itself. So let's go back to the Maxwell's equation. We need to get this equation, right? Once we get the generalized form of this equation, then that's the Green's function we want to solve for. And once we have the Green's function, then it's again the tedious part of doing it for specific configurations. What happens for this case? What happens for that case? And in electrostatics and magnetostatics itself, the exact solutions are very rare, right? Mostly it is spherical and planar. That's it. Right? Most of the time, exact solutions are very difficult. In electrodynamics, it gets much more worse. There are no exact solutions. Right? So there's no exact solutions available. So for any configuration, in the case of electrodynamics, the only simplest scenario when you move with uniform velocity, that's the only solvable problem. Rest everything is too hard to solve. So we will, instead of solving for configurations, we will talk about regimes. In what situations can we make some approximations, and then can we solve? And one of those standard situations is radiation, where your observation point is very far away. If you go extremely far away, then your solutions become solvable, or they have very simple solutions there. But let's construct the equations. Maxwell, let's go back to Maxwell's equation. We have L dotted with epsilon naught E is equal to rho. So magnetic field is equal to 0. So cross with the electric field. The curl of the electric field is the time derivative of the magnetic field, and L cross H equal to the time derivative E plus J. And H here.
Del cross is negative.
Negative. Very good. Thank you very much. And this is D over U naught. Good. Thank you for pointing that out. And let's immediately do pretty much what we were doing earlier. Also, we want to define potentials, right? Scalar potential and vector potential. Let's how do you define your scalar potential? You first, let's say you go from the divergence of the magnetic field, right? If you say that divergence of a vector field, remember, is everywhere in space, it's not just at one point. If you say that divergence of a field has to be equal to 0, you're putting a huge constraint on that field. Like not every field can have the divergence to be 0 everywhere. If you're not staying at one particular point, at everywhere in space, it cannot have a divergence. That's a huge constraint you put on the field. And one of the solutions, in fact, one of the only reasonable solution is that immediately it means that the magnetic field can be written as a cross the curve of another potential, right? So if you have magnetic field of this form, then this will immediately satisfy this. So what we are doing here is that writing the solution in terms of another solution. A magnetic field is what we are interested in, but we are saying that whatever is the magnetic field, it must have this form because that will immediately satisfy that divergent string nature to that. So this is implying this. Is that clear? If similarly, for example, curl was equal to 0, if curl, like notice what we have done is in statics, this is equal to 0. This is in general always true. This immediately implies B is equal to curl of. But in statics, what we have is curl of the electric field is 0 in statics, right? And what does that imply? If the curl of the electric field is 0, what does this imply? Immediately, everywhere in space, this has to be equal to 0. What does that mean?
Gradient cross the potential.
Or gradient
Is
of
gradient.
the potential, right? This implies that electric field has to be a gradient of a scalar quantity. That's what you mean.
Yeah.
Yes. Yeah. Very good, except you put a negative sign also. Okay. This is the same statement as in classical mechanics or in Newtonian physics, you see the same thing. Or what is the, maybe I should ask you, what is the statement in Newtonian physics that has the identical statement? That is, this is electric field. This could be the force is equal to negative gradient of potential energy. Very good. So the potential energy exists. You can associate a potential energy to a force only when
Force is conservative.
conservative, or another statement now is it is curl of the force is 0. If it's a position dependent force, then the curl of that force has to be 0, which is a statement of conservative force. Very good. Only if the force is conservative can we define a potential energy, and the more technical statement of the force being conservative is that the curl of that force, that position dependent force, should be equal to 0, right? So that's all there. So now, but we are not interested in statics, right? That's not good enough. So but we still want to work with this curve. We want to do something along that line. So what you do is, let's do what did I want to do? Yeah, so now that we have B is equal to curl of A, substitute this in the second equation. So substitute this in here, and I learn that curl of electric field, put it on the right side, plus the time derivative of the curl of the vector potential is equal to 0. But that should be a true statement. Write this as the curl plus time derivative of. What can you conclude? Remember, I just now had a discussion on what it means to say that divergence of a quantity is equal to 0 everywhere in space. if the curl of a quantity is zero in everywhere in space, then it immediately implies this. I have the curl of a quantity is equal to zero everywhere. What does this imply?
E plus dt, dA dt is
Very
greater.
good. So this whole quantity, earlier I just said E is equal to this. It just means that this whole quantity has to satisfy that. That's the generalization to dynamics. This is no more statics. Right, electric field. Has a potential, has a scalar potential and a vector potential that can create the electric field. And this is the content of Faraday's law also in a sense, right? If you have a change in magnetic field, you can create electric field. All the sources of our energies is dependent on that, right? When you have a electric dam and a dynamo is working, you somehow want to rotate something, a magnet somehow, and that creates an electric field. Most of our energy is created by that. Eventually, somewhere you will convert that into electric energy using that process. So that's your generalization from statics to dynamics. That's one important step that you make. So in statics, it's gradient of potential. Now it has a vector nature also in there. So what's our equation for pi and a, right? That's what we want to calculate. Any questions at this stage?
We have the curl of P plus the y over the T, right? So for electric field, we getting potential, the gradient of potential. So what about the vector potential part inside now?
Notice this is statics, so this is wrong. This is wrong. This statement that we wrote all the while is wrong in the sense that it is statics. If you're not doing statics, you cannot use this.
Yeah.
So this is the generalization of that.
Oh, that's all. This is the correct one.
This is the correct answer. In the static case, you drop this.
Oh, okay.
Like time derivative, A is not changing with time, so you drop this. That was a mistake.
In the first place, we are not thinking like from that comes to this, but it should be this from that.
Exactly. Right. So this is not correct. Right. So that's the correct one. And from here, static, you make this T A independent of T, and then that's basically the whole equations decouple, right? When there is it's static, this goes to this is the connection, right? B can create electric field. Like this goes away, that coupling is not there, and this goes away. And the moment they don't imply each other, which is basically Faraday's induction, then you couple, decouple electricity and magnetism. So this is decoupling happens only in statics. But now we are talking about the coupling, where this will create that and that will create this. And the best is that they can sustain each other without the charges, right? That's light. Like usually we say electric field requires a charge, magnetic field requires a current. But the best interesting situation is where electric field and magnetic field can sustain each other. You just have to change each other in such a way that electric field creates magnetic field and magnetic field creates electric field, and that's light. There is no charge, there is no current for light. Of course, it's created using antenna where there is a charge moving, but once you have created it, it can sustain on its own. It can survive that it need not decay. Okay, but that's and these equations here. Now generalize them. So we have this equation. So that's your two definitions, right? That's your definition of vector potential in terms of magnetic field, and that's your scalar and vector potential in terms of the electric field. Substitute it back, and we get our equations of motion for your scalar and vector potential. So let's start with which one? Let's start one of them. Yeah, so let's substitute things here in the last equation. So that's your del cross B. B was del cross A. And I had a mu naught also, I'll multiply it all the way to the right. So that's mu naught, epsilon naught, and time derivative of the electric field, which was minus gradient of phi minus dA by dt. And plus mu naught times J. Use the vector identity, that's minus, no, plus gradient of divergence of A minus of Laplacian A is equal to minus, so that's nothing but 1 over c squared, right? So it's minus 1 over c squared. Second derivative with time of A plus, no, minus of 1 over c squared. Although I don't want to write it, d by dt. Divergence of the scalar potential plus mu naught J. I think I got it. Let me rewrite this in a manner. So it's minus del square. Take the time derivative to the right. Okay, and this time I have both position and time here, and that's equal to mu naught times J. And I have, let me write to this, minus of the divergence of A. This is plus 1 over c d by dt pi over c. I wrote the c square in a particular form. That's just a way of writing. Okay. If t was if we are doing statics, what happens is that this is not there. Right? This term is not there. That term is not there, and in statics, notice you get this equation. This is your equation in statics. How do I go from here to there? So statics is when the second derivative is not there, time derivative, all that goes away. So that's minus del square. A is equal to mu naught times J and minus of divergence but that's not this. What happened? What's wrong? Right, this is on this, right?
Del dot A is 0,
And why is that delta A is 0?
statics.
Why should it be 0 in statics? Why should A be divergence less?
You don't have any source
No.
in the static.
Something more than that.
Scale. Gradient of a scale.
Say that again?
Delta T is a scalar, right?
Yes. Delta A is a scalar, so what? A is vector.
Vectors.
A is a vector, yeah.
Unitary.
Or maybe the way you want to think about it is that whenever we have an electric potential, let's say scalar potential. Let's go back to statics, right? Statics, so whenever, yeah, if electric field in statics is negative gradient of phi. Derivative of something misses a constant, right? You can always miss a constant here and I won't know about it. So whenever I take the liberty to go to a potential description, on a vector description, I'm sacrificing that uniqueness. I will have a solution, I can add a constant to that. Notice this is a constant in the whole field, not just one point. And I'll still be fine. Okay, because the derivative will kill that. So there is a non-uniqueness as far as phi goes. When you talk about a vector field, so now we have a vector potential, which is the curl of that. That's much more than that. It is not just a constant that you miss. You can add a whole gradient of an arbitrary field. I can add, for example, this is a solution. What else could be a solution? I could add plus the whole of a divergence of some arbitrary function, lambda. This is arbitrary. Like a constant is arbitrary. A whole function which could have all dramatic structures in there. The only requirement I say is that I have to be judicious enough to make sure that it is the curl of the, sorry, the gradient of that I add on to that. And this curl will kill it. So magnetic field will not see that. The constant here, so when you ground in the electricity, I could have chosen any ground I want. I can reset that ground to 1000 volts. Electric field will not care for that, right? But now this is much more than that. You're saying that I can add any function to that, and the magnetic field will be the same. So in that sense, the vector potential is not really measurable. It's not a experimentally, if you were to check, if you were to try to do this, because this has a lot of arbitrariness in there. So whenever you have an arbitrariness, you set it, right? You say that, let's say that we set a ground, right? Ground voltage. When you're doing an experiment, you'll say that, oh, that's my ground, that's voltage V equal to 0. In this stage, you have to do much more than that. You have to set the lambda at everywhere in space. And one of the choice, this is called a gauge. So there's a gauge dependence in this potential. So you have to set your gauge. And this is the choice of the gauge. You set this to 0, so gauge choice. So whenever we wrote things down here, this was in a particular choice of the gauge, and that was chosen to be del dotted with A equal to 0. Okay. A very particular choice, and that was called the Coulomb gauge. Okay, so that's del dotted with A, that's called the Coulomb gauge. There are various other choice of gauges you can make, and that's perfectly fine. As far as it's a consistent gauge, you're good. Okay. Any questions there? Any comments? We want to do the same thing here now in dynamics. That was statics, right? In statics, we had a choice, we worked with that, and as far as you know that that choice has been made, that's good. Here we make a exactly similar choice. So this is now statics, right? I'm leaving statics now. This was just for discussion. I brought in statics. Now I'm going back to dynamics. This is my main equation. So now I choose a gauge, which is the Lorentz gauge, not the Coulomb gauge. Okay. Make a choice, and in this case, del dotted with A plus 1 over C d by dt and phi over C. That's chosen to be 0. Okay, and that's it. It's not that you have a lot of freedom in choosing a gauge, since you're setting the origin. You have to be very careful. Once you set the gauge, that's it. You cannot do this twice or thrice, and you cannot keep doing it. It's good to see we have in everything we write we have now introduced relativity. And it should be possible to write this in a relativistic language, right? Remember your A was vector A mu is equal to phi and A. Right. Scalar potential is the zeroth component of A mu. And A is this is the 4 vector potential. And what is missing in this? C, very good. So if there's a C in here. And d mu is equal to time derivative and the gradient. Okay, dimensionally, if you want to match it, you need a C. So there's a C in there. And if you try to do this, then you immediately see that, oh, that's nothing but I. So this is I. This is AI, right? An index notation. And this is nothing but plus D0. And that's A0. And that means to say that in the index notation, the Lorentz gauge has this compact form that the 4 derivative of A mu is equal to 0. But that's just compact. As far as physics goes, it's the same equation. Nothing has changed. It's just a notation that is more compact. Okay. In that choice, the right-hand side goes to 0, and we have our, this whole thing is gone now. So our equation is this. And we want to find the Green's function for that. But before we go there, let's get the equation for the scalar potential. So this is the vector potential for the scalar potential. Notice now we are having time dependence in there. Any questions at this stage? Okay. So let's do scalar potential. Question, right?
No. I'm just thinking. No.
Okay. Aryan? Okay, so scalar potential, how do you get scalar potential? We again, yeah, it's probably here, right? We substitute this in there. So put it in the first equation. We have gradient dotted with epsilon naught times the electric field is negative gradient of phi minus of dA by dt is equal to rho. That's the same as, let's do something. We have minus gradient square of phi minus of time derivative of the divergence of A is equal to rho over epsilon naught. But the divergence of A is nothing but using the Lorentz gauge. Since I'm working in the Lorentz gauge, I can replace this with the time derivative of the potential. So that is a condition or a constraint you're putting in the choice of your potentials. And in the Lorentz gauge, you have minus del square phi plus now d by dt. And you have 1 over c square d by dt of phi is equal to rho over epsilon naught using Lorentz gauge. And you get your equation. That's del square. I like to write this as minus 1 over c square scalar potential now has both position and time dependence. 1 over epsilon naught. So we're talking about the source having both position and charge, and just to write that in the same. And the similarity is just visually there, right? We don't have to even say that. The differential equation is exactly the same for the scalar potential and the vector potential. Sources are different, but that's there in statics also. This is the generalization. If you want. Let's make it a little more. Even the mu naught is not, that's not really convenient there. Let's really fix that mu naught. Epsilon naught is nothing but 1 over mu naught times c squared. So let me replace this 1 over epsilon naught with mu naught and a c squared. In fact, let me write this as, I want to write two of the, I want to write this as c mu naught c. I want to keep that, so replacing that here. You cannot erase on your notes. So this is mu naught times c. There's an extra c, but that I bring that down here. C. Okay. And that was purposefully done. Why did I do that? Because this is the 0th component of A. Right? In this form, this is the 0th component of A. So this is equal to now and 4 vector notation. So let me first go minus del square. This is A mu. When mu is equal to 0, I get this, mu equal to I get this. And that's equal to mu naught times J, vector, 4 vector, J mu of R, comma T. Maybe mu and mu comes at the same place, since, so let's make it alpha. So clear? When alpha is equal to 0, that gives me this equation. When alpha is equal to this space index, it gives me these 3 index. So it's all the same. But then when we are really making it compact, why not make this also compact? This is nothing but minus d mu if you want, times A alpha is equal to mu naught J alpha. In fact, d mu is often recognized as del square, so that's del square A alpha. So that's the equation you want, and so static Green's function, you usually don't say static. I mean, it's just Green's function. You don't say static, okay, but I'm just writing it so that to emphasize that. Green function. Can say greens if you want, but green function. Okay. And that's. The equation is minus del square and. E. R, no time involved. And that is an R minus, if I keep that. Minus R prime actually. If I keep the source somewhere else, that's equal to. And now we are going in dynamical situation, and that is called retarded Green's function. This is one particular solution, but that's what we will use. If you have done math methods, I think some of you have done math methods, remember, this was only one particular scenario. We had retarded, and what were the others? That was Feynman Green's function, the Wheeler Green's function, and that is futuristic Green's function also. So, this is retarded Green's function now, that's what we are interested in, and that's this equation. And that's what we are going to try to solve in the next lecture. It's del square minus 1 over c square g. So this was g naught, so this is now no more naught, so this is generalized. E minus t prime. That's equal to space. Hopefully captures in that. Yes, a little bit. And there is time also now. The delta function in time also. That's your solution that you want to find. That's the equation you want the solution for. Again, if you were to have a solution as such, so what is the solution for G naught? That's clear, right? G naught R minus R prime is equal to the factor of 1 over 4 pi 1 over R minus R prime. If you choose R prime to be 0, this is just 1 over R, right? That's what we start our introductory electrodynamics with, right? Electric potential is Q over R. Same idea. That's what it is. What do you expect this to be? What should be the generalization of this? Any experience? So, like, it's not that what we learn next lecture or next week. This, what is this equal to?
Should be the same thing
Same thing? No changes?
with the add time.
At time, yeah, what is the time? Yeah, exactly. Yeah, that's so. So I think that's a good point to make, that it should have almost the same structure, because if you set something to 0, that should come up. That means statics should give you this. So the denominator actually will stay the same. What changes?
Delta function.
Delta function of, that's correct, actually good.
T minus T prime.
T minus T prime. No, that's not correct. This is what was, this is statics, basically, if you want, that's statics. Right, there's time dependent. This is pretty much this, that's statics. And we'll see why that is static. So what changes? What's the big deal with? What is retarded? Maybe that word helps. Retarded, of course, has a meaning with the mental instability also, right? But that's the retarded in the sense
Delayed.
there's a delay. There's a significant difference from Newton's perspective of how things happen and Maxwell's perception. Like what did relativity bring in, that everything happens with speed of light? Like what we see of stars today happened sometimes billions of years, at least 4 light years before. You're not seeing today's star, you're seeing 4 years back in time. If we watch the closest star. If we go further back, sometimes we are seeing millions of years back in time. So there's that's called retardation. Like, it's not cause and it's a cause and effect. There's a delay in there. That delay has to be accounted for. So it's not today's time we are watching, it is something else. How much is the delay? How far you're? Right? If you're 4 light years away, so that time delay is distance. How far you are divided by c. It's the light that is. So this is the only change you need to make. And that's going to be a solution, but that's not obvious. We'll derive this. Okay, this is the most important equation in this course. We'll derive this, but that's the result. That's the only change. Everything else stays the same. And the retardation is implicit, it's a mathematical truth in a sense, you cannot escape it.
To counteract. the way-
Exactly. That's the interpretation, but this is how the solution will come in. Right, but we'll solve that. Not in the next lecture, next lecture, we're off. Right, I'm taking a break. Next Thursday, 1 week from today, 1 hour or 1 hour and 15 minutes behind. And we will see that. And that's all. We'll stop early for a change. Compensate for many of the extra, but that doesn't compensate actually. That's a change. Thank you.